have their answers in themselves. It's not difficult to understand why we have this minus sign here. Let me give you an idea of how can you account for this minus sign. I'm going to draw the wave at two instances in time. X, some y. Now remember, I'm talking about propagation along one dimension only, along x dimension. And y is not a spatial dimension. I'm taking y to be the amount of the disturbance. Okay? So y is not the x-axis, the y and the z-axis of a Euclidean plane. Remember that. So I'm talking about propagation in one dimension only, for simplicity. Now let me draw the wave at time t equals 0. Okay. Suppose the wave is such that it looks like this. Suppose. Okay? Suppose this is the wave at time t equals 0. Now what I am claiming is that the disturbance or the wave is propagating to the right. That's what I am claiming. So now I would like to draw the wave at some later time. Let me draw the wave at time t equals t by 4. After 1/4 of the time period. So now if I look at this expression, y okay, let's forget about the math first. What would be the picture of the wave after a time equal to 1/4 of the time period has lapsed? The wave is moving to the right, to your right. So it has moved a quarter cycle ahead. So now if I were to draw a picture of the wave, this is what the wave is going to look like. So previously at x equals 0, there was a node. There was a 0 of the disturbance. Now after some time has elapsed, the wave is moving forward. So this entire white wave has moved towards the right. And now this cusp here, this trough here, this bottom point here has reached x equals 0. Okay, so this is how the wave is propagating forward in time. So let's look at the value of the wave at x equals 0. So for time equals 0, the value of the wave at x equals 0, time t equals 0 is simply a sine of 0, 0, and for the white wave, I'm taking my reference to be 0. So this is sine of 0 to 0. So the value of the disturbance at time t equals 0, x equals 0 is 0. Now let's look at the yellow after a time capital T over 4 has lapsed. Let's look at the value of the disturbance at x equals 0. Y still at x equals 0, but after a certain lapse of time, this becomes a sine of, now here I still have 0, minus 2 pi over capital T, small t is now t over 4, just, right? It's a sine of minus pi over 2, which is minus a. So now at this point, after this time, the value of the disturbance at this location is -8, and indeed it is. So this is the correct formula for a wave that is propagating forward, that is propagating to the right. If I have a wave that is propagating to the left, I will just put a plus sign here. Okay? So I have a logical argument of why I have a minus sign for a forward propagating wave and a plus sign for a backward propagating wave. Yes, you had a question. The phase is our choice. Whatever our heart desires, we can put the phase. I'm choosing that at time t equals 0, x equals 0, this disturbance is 0. I'm choosing that. This is the picture that I've drawn. This is my choice. If I were to put my origin here instead, then my phase would be non-zero. But I'm putting my origin here for simplicity. Okay? Yes. Right, so now whatever is inside the argument, all of this is a phase. There's no difference dimensionally between this, everything is contributing to the phase. This is a reference phase. Right? This is a reference phase. But omega t is also a phase. Tx is also a phase. All of this is contributing to a phase. And there are different ways of having a phase. One is just a background reference phase. This is the choice of the origin. This is the phase that comes out because of the temporal progression. This is the phase that comes out because of the spatial propagation. Okay, all three of these are phases. It's just that this is a reference phase, a fiducial phase. Alright, so this is the mathematical form for a wave. We also have to talk about the particle, by the way, if you were to talk about wave-particle duality. Alright? Now the thing is that you introduce more math not to make life difficult, but to make life easier. Okay? So we are averse to mathematics, so we are afraid of mathematics because it's the first time that we are seeing it. But actually we introduce math to make our subsequent lives easier. Now this is a trigonometric function. And generally it is customary in all of physics to work in complex numbers. So this wave can be represented by a complex number as well. Okay? Remember, this is a spatio-temporal wave which changes with x, changes with time. Now, I would like to express this wave as a complex number which has a real part and an imaginary part. Alright. Is everyone familiar with complex numbers? अच्छा, जिन्होंने नो कहा है वो ताकि मुझे अंदाजा हो जाए कि वो कितने हैं, मैं उस हिसाब से फिर क्लास में उनको बयान करूँ। कितनों ने कॉम्प्लेक्स नंबर्स पहले नहीं देखे? ठीक है, और भी यहाँ से आवाज आई थी तो there is a minority, but nevertheless there are some people who haven't seen complex numbers. So let me spend 4 or 5 minutes on describing complex numbers. But I will always try to talk about waves. Yes? This stuff. So this is with respect to space, but the white and the yellow curves are at different times. Yes. No, it's not time. So the white curve represents the graph at one time. The yellow curve represents the graph at a later time. As a human being, limited by biology, I cannot draw spatio-temporal graph on a blackboard at the same time. So So now what I would like to do is I would like to express that mathematical form in the form of a complex number. Alright? Now, alright, y equals a. Instead of sine, I can also write cosine. Doesn't matter. I can just change the phase. Sine and cosine are on equal footing. So I can write a way that a cosine of ax minus omega t plus phi. Correct? I can write a sine or a cosine. If I just change the phase, I choose a reference such that the phase is pi by 2, I can convert a sine into a cosine. Alright. Now this is a real number. And physics is real, right? So whenever you're measuring the displacement of a boy on a water wave, you can have a meter scale and it gives you a real number. If you're measuring the electric field, suppose you have an instrument that measures the electric field for a light wave, it gives you a real number. If you're measuring the sound wave to a pressure transducer, it gives you a real value. So all of these are real numbers, right? Physics is real, it's not imaginary. However, mathematicians would like to make our lives easier sometimes, only in rare occasions. So now what they would like to do is they would like to represent this real quantity by a complex number. Now remember, complex is not complicated. Complex is a name given to a special kind of numbers, which has a real part and an imaginary part. And imaginary is not really imaginary. Imaginary, real, complex, these are just words that have stuck to our vocabulary, to our mathematical vocabulary. Okay? Now, if I would like to represent this number by a complex number, what generally is done is, this is just a scalar. Okay? So I write this as A. And instead of this trigonometric function, I write it as an exponential function. E raised to the power of this argument, kx minus omega t plus phi, and I put an iota with this. E raised to the power of iota kx minus omega t plus phi. Okay? Now this is a complex number. Alright? Does everyone know what iota is? Iota is an object. An object whose square is minus 1. Now this number here is a complex number, and it can be represented by a vector. I can draw a diagram Let's draw a diagram. I'm keeping some math here. This is called an Argand diagram, in which this axis, this horizontal axis, is a real axis, and this axis is an imaginary axis. And this object here is a point on this plane. Now, where is that point on this plane? Its distance from the origin is given by A. So this point can be anywhere on a circle whose radius is A. But where on this circle? That is determined by the argument of the exponent, which all of this is also called the phase. All of this is the phase. All of these three terms have the dimensions of phase. Now, where this point is located on this circle depends upon the phase. It could be anywhere. It could also be on the real axis. It could also be on the imaginary axis. It could have a real component and an imaginary component. Suppose the point lies here. I can draw a vector from the origin to the point, and this point or the vector represents the complex number. Alright? And now that I got this theorem, I can draw a projection on the real axis. This is the real component of the number. Whereas, if I draw a projection on the imaginary axis, this is the imaginary component of the number. Alright, now let me take a simple example. Let me take the number A, E, I, 5. Forget about the kx and the omega t for the time being. The Argand diagram, a real axis and an imaginary axis. A circle of radius A. If my phi is 0, alright, then I have e raised to power iota into 0. What is e raised to power 0? 1. I'm just left with A. A is a purely real number. So I get this point. And I get this vector. Yes. Now, this is a complex number. I would like to represent this number on the diagram. Now, A is the circle's radius. I would like to pinpoint where on this radius does this number lie. Now, that depends upon the value of the phase. If my phase is 0, I get A e raised to power I times 0, which is A e raised to power 0. Anything raised to power 0 is just 1. So I get A, which is just a real number. Now that real number must lie on the real axis. Therefore, I must lie over here. Okay? If my A is positive, by the way. If this A is positive, I lie here. If this A is negative, I lie here. I lie on the real axis. Okay? So phi equals 0. If phi equals 0, my vector, my complex number is represented by this arrow. If my A is positive, by the way. Suppose phi is pi by 2, is 90 degrees. Now I have A, phi is pi by 2, so my number is AI pi by 2. Now what is exponent? Remember, this is something that you need to remember. E raised to power I theta is cosine of theta plus iota sine of theta. Alright? Do you know this formula? Never have you ever seen it. Alright? I'll explain it in a minute. But let's, for the time being, observe that there's a formula like this. Okay? Now, according to this formula, A into E raised to power iota pi by 2 becomes A cosine pi by 2 plus iota sine pi by 2. Now what is cosine of 90 degrees? 0. Sine of 90? 1. So this becomes 0 and I'm left with iota times a. Now is this a real number or an imaginary number? Imaginary, purely imaginary, it doesn't have a real part. It just has iota multiplied with a scalar. It's a purely imaginary number. So this point on this diagram must lie either here or here on the imaginary axis. Right? If A is positive, it lies here. If A is negative, it lies here. So this number is represented by this vector. So this is how you represent a complex number on this arcand plane. Now, if I have an arbitrary angle, theta, if my phase is arbitrary, phi, arbitrary, I will lie anywhere on this circle depending upon the value of phi. If my phi is 0, I lie here. If my phi is 90 degrees, I lie here. Suppose my phi is 45 degrees. Right? So if my phi is 45 degrees, phi is 45 degrees, then my number is A, I is for pi by 4, which becomes A cosine of pi by 4 plus iota sine of pi by 4. This becomes, what's cosine of 45 degrees? 1 over under root 2 becomes A 1 over under root 2 plus iota 1 over under root 2. Now what I need to do is, this number now has a real component as well as an imaginary component. So it must lie somewhere in this quadrant. Right? So I can draw a vector which is at an angle of 45 degrees from the real axis. So this is the vector that I draw. This vector represents this number, this complex number, and if I take the projection on the real axis, then this length, what's the value of this length? A over under root 2. So the real component of this number is A over under root 2. And if I took the imaginary component, which means I project onto this axis, then this length is A over under root 2. The length is A over under root 2, but along the imaginary axis. So now I have a complex number which has a real projection and an imaginary projection, which has a real component and an imaginary component, part real, part imaginary. Alright? And this is where this formula comes from. So this is just the real projection. If you drew a right angled triangle, the real part is simply cosine theta and the imaginary part is sine theta. Do you agree with that? This is where this formula comes from. So now I have given you a lightning fast introduction to complex numbers. Really lightning fast. This is almost 90% of what you need to know. Yes. Okay, we have about 40 lectures to learn about the importance of numbers, right? We learn about it, right? I will do it. Just have some patience, please. Yes. Studying it. Yes.
Sir, is this A raised to I by and it's just an expression that it is an equation of y.
Equation of?
Y.
I'll explain that. What does this have to do with the wave motion? Alright, so let's move on. Yes? But the length is A over under root 2 along the imaginary axis. This is the length, the projection. Alright, now my next task is to build a bridge. Excuse me. Right at the back. Unfortunately, the teacher is at a special point. He can see each and every student. Alright. Right at the back. Excuse me. तो पीछे देख रहे हैं. Now I have to build a bridge between wave motion and the kind of expression that we have here. This is our formula. If I have cosine of something, the cosine is just the real component of a complex number. Agreed? And if I have sine of something, it's just the imaginary component of a complex number. That's it. Something which is cosine is the real part, something which is sine is the imaginary part. Okay? So now if I would like to look at this expression is just the imaginary component of a real number, of a complex number. So what I could write is, if my wave is represented by a cosine of kx minus omega t plus phi, then this is just the real component of a complex number, and that complex number is a e raised to power iota, all of this, kx minus omega t plus phi. कुछ भी नहीं किया. I've just identified the cosine function with the real part of a complex number. That's what a complex number means. It has a real part and an imaginary part. The real part is the cosine of the angle of the phase, and the imaginary component is the sine of the phase. That's all there is to it. So it's just a notational convenience for the time being. Nothing beyond notation. Alright? If I had a sine of kx minus omega t plus phi, this would be the imaginary component of the complex number. Now, there's only notation here, right? Nothing beyond that. Alright? Now, why do we have to undergo this pain of changing the notation and going into the abstract concept of complex numbers? The reason comes because out of mathematical simplicity. We will learn about, have you learned differentiation and integration? It's very easy to differentiate and integrate exponential functions. Okay? For example, the derivative of eikx is the number itself. With a factor of ik. Or the derivative with respect to theta of ei theta is I. So it's very easy to manipulate these complex numbers. Suppose alright. So now what physicists generally do, they don't want to write the imaginary and the real parts over and over and over again. They would just write that my wave is simply a ei kx minus omega t plus phi. This is their wave, y. And it's understood that the wave is either physically it's the real part or the imaginary part. Okay? And we just take the real part, for example. The sine and the cosine can be inverted by changing the value of phi by the reference phase. So they just say that the wave is an exponential function. Only notation, mere notational simplicity At the moment, I agree and I admit that instead of notational simplicity, this might look like notational complexity. And I admit it, at the moment it might seem this to be the case. But take me on my word, as we go through this course, this will turn out to be a blessing. We don't want to write sine and cosine over and over again, we just want to write exponential functions. So there are certain subjects that come with the passage of time, that assimilate into your blood with the passage of time. This is one concept that comes with time. Alright? So I've introduced complex numbers, and the wave is just a complex number. A sine wave is just a complex number. And I know that if I were to do an experiment or if I were to do calculations, at the end I have to take either the real part or the imaginary part. I can take either, because changing the phase will convert the real to the imaginary part. The sine is converted to the cosine. Now, this is what I would like to talk about waves. Now, I would like to talk about a particle. What's a particle? Alright, just like we did for waves, what is the idea when you hear the word particle? What idea comes to your mind? Yes, at the back. I like hands risen at the back. Yes.
Something which has mass and occupies space.
Which has mass and occupies space. Alright. By the way, in modern physics, not all particles have mass. A photon, for example, doesn't have mass. Or it occupies some space, which is another way of saying it is localized in space. Look at this word, localized. This wave, it's not localized in space. It exists, if it's an ideal wave, an ideal plane wave, it exists everywhere in space. So this x-axis goes from minus infinity to plus infinity. It exists everywhere in space. So it's not localized. This wave is delocalized. It's not localized. However, when we talk about a particle, as my friend at the back has just described, we come up with the idea of something that is localized in space. It only exists at a certain region in space, which has a boundary, right? So there is a region which, if you fall into that region, you are inside the particle, and if you fall outside the region, you are outside the particle. This is our concept of localization. So generally we think that the particle is localized in space. Good. Anything else? Yes. A particle has momentum. Exactly. A particle has momentum. For example, if I'm standing here and if I'm struck by particles, God forbid by say bullet particles, the momentum will be transferred to me and I'll change my momentum. If I have a solar panel on a Hubble Space Telescope, light is falling onto the solar panels and the telescope's panels are going to be affected by the momentum. So the light is carried by particles called photons and they carry momentum. The momentum of the photons is called radiation pressure. So a particle is generally considered to be something that carries momentum. Anything else? Yes. Now this is a question, it's an excellent question. The gentleman has asked the question, a particle, a photon doesn't have mass, but it has momentum. Do you understand the question? Excellent question. So a photon doesn't have mass, but still it has momentum. And generally, momentum is considered to be P equals mv. Now what's the speed of a photon in vacuum? A photon moves with the speed of light, alright? Now is C finite? C is finite. It's a finite speed. And in all frames of reference, light always moves with this speed. But the mass of a photon, I claim, is 0. So how can it possess momentum, a non-zero momentum, when it has a finite speed and the mass is 0? That's the question, a very good question. Let's look at an answer. Anyone would like to propose an answer? Yes. That's alright, so now you're getting into the nitty-gritty of wave-particle duality. These are very good questions. Does a wave have a momentum? Yes, it does. That's the de Broglie relationship. We're going to talk about it. Well, it's possible. It's possible. Very good questions. This is the kind of discussion we'd like to have. Yes. Yes, we can. So excellent. So there are different ways of answering this question. This gentleman has come up with an excellent proposal. The photon carries energy, E. Now we know from the Einstein's relationship that the photon is also a wave. It has a certain frequency. The color of the photon, that determines the energy. Now this is a purely wave concept. Energy is both a wave concept and a particle concept. Now Einstein proposed that the energy must be given by mc squared. Now what we could do is we could find out the effective mass of a photon. But the problem is that it doesn't have a real mass. Okay? So if we were to equate hf over, if we were to find this, hf over c squared, this will be like the effective mass of a photon. Alright? How do we know that the photon has an effective mass? Because it is affected by gravity. Photons are affected by gravity. This is the phenomenon of gravitational lensing. But the most appropriate answer to the question that this gentleman has asked is that when you have particles moving at or close to the speed of light, the formula for the energy slightly changes. And it's given by the following. This is the formula for the energy of a particle that is moving at or very close to the speed of light, that is moving at relativistic speed. So a photon has mass equals 0. So this term goes to 0. Still it possesses momentum, V. Alright? So when you talk about particles moving at or close to the speed of light, the concept of momentum changes. It's different. Alright? And this is a relativistic formula that needs to be used. Alright. So this was a slight digression, which is a good, nice, healthy digression. But the concept of a particle, I think, is clear. Something that is localized in space, something that you think has mass, something that you think has momentum. For example, I would like to say that a particle, conventionally we think of a particle as a lump of energy. Something that is lumped together, that is confined in a region of space and time. A packet of energy, a corpuscle of energy, okay? A bunch of energy. For example, if you take all the energy in this room and bunch it together so that it appears at one point in space and one point in time, generally we refer to this as a particle. For example, if I have a person sitting in a boat and there is water, and there are water waves of this kind, and the wave is propagating with a certain speed, then this person sitting in the boat is going to buoy up and down, is going to undulate in a vertical to and fro motion, and he or she is going to say that I'm being hit by a wave. I'm seeing a wave. This is what he would, if he's not a physicist, this is what he would claim. I'm seeing a wave. I'm feeling wave motion. However, if the same person is hit by a tsunami of this kind, a small, congregated, lumped form of oscillation, lumped and energy lumped together only in this region, and this pulse is now moving with a certain speed. At one point in time, this person sitting in the boat is calm and steady, is taking a nap. Suddenly this bunch of energy, this capsule of energy reaches this person, and he takes a sudden jolt in the upward direction, and then he comes to rest. He would treat this as if a particle has hit the boat. So this is our general English language understanding of what a particle is, or what a capsule is. Now the question that I would like to ask is, what is matter? Whether it's a particle or a wave, and you're already familiar with this concept. Now this concept was first introduced, this duality was first introduced by Broglie in the 1920s, and he introduced the concept of what is called a pilot wave. Now Broglie mentioned, he proposed that every particle has a wave associated with it, and he calls the wave a pilot wave. For example, suppose this is my particle. It could be an electron, a proton, a neutron, or a piece of chalk. It's my particle. Now when this particle moves in space and in time, so this particle is now propagating in space and in time. Now I'm drawing a picture of a particle. Please, no commotion. I'm drawing a picture of a particle. This is the space axis. Now the particle at time t equals 0 is here, at some later time it's here, at some later time it's here, later time here, and so on. Now what Broglie proposed is that this particle harbors with itself, it carries with itself, possesses a wave. And he named the wave a pilot wave. Now what does a pilot do? A pilot steers an aircraft. What he proposed is that this particle is being steered by a pilot wave, and that pilot wave has the form of a pulse. So this is the pilot wave associated with the particle at this instant in time. At another instant in time, the pilot wave has moved forward and it's localized in space. The wave is localized in space. This is the giant leap of de Broglie. He mentioned that since the particle is localized in space, the wave is also localized in space. Now this pilot wave is not a sine function, but still it's a wave. And we can build this wave packet or pulse out of sine waves. You don't know how to do that, but I'll teach you how to do that. So at some later instant in time, the pilot wave associated with the particle has moved forward in time. So this particle is being handheld. Suppose you're the particle, I'm the pilot wave, I'm holding your hand and I'm steering you through space and time. So this is the concept of the pilot wave. Associated with every particle, there is a pilot wave. Now if you look at the Bohr's model, you all learn about the Bohr model. If you look at the orbit of an electron around the nucleus, in the Bohr's model, the electron is going around the nucleus with a certain linear speed v. Now the idea of Bohr was in compliance with de Broglie relationship. Actually, Bohr proposed his idea before de Broglie. He also proposed that associated with this particle, there is a wave inside the orbit of the electron, which is steering the electron inside the orbit. And Bohr's idea was that if this were to be a stable configuration, then the circumference of this orbit, 2 pi r, must be equal to an integral number of the wavelengths. Correct? And from here he mentioned he was able to derive that the angular momentum mvr is quantized. Alright? So in the next lecture what I would like to do is, we'll have questions afterwards, but half a minute please. Half a minute please. The lecture is not yet over, we have 5 minutes. In the next lecture, I would like to tell you what is an electron. Thank you.